Thank you. So first of all, it's a pleasure to be here today. Thank you very much for the kind invitation. I'm Matija, as Thomas mentioned, one of the co-founders of Gideon Brothers, and today I'm gonna try to give you a very brief overview of what is a very exciting space right now. We're talking about vision-based autonomous navigation technologies for low-speed robots. So as you are probably aware, as my has been already mentioned in the previous presentation, vision is becoming quite a critical component of robotics systems nowadays. And we at Gideon Brothers specialize in building autonomous navigation capabilities for low-speed industrial vehicles, primarily based on visual information itself. So that's what I'm going to be talking about here today. Unfortunately, we won't be able to get into a lot more details because it's a very wide set of themes and topics. So I'm going to be quite open, of course, to dive deeper into the details later in the follow-up sessions. So first of all, just like a very brief context to kind of describe or explain why we actually started tackling the problems we're tackling right now. We're now currently in an era where, of course, our global supply chains rely on all sorts of mobile industrial machines, all sorts of different mobile equipment, whether we're talking about manufacturing plants or logistics warehouses, whether we talk about forklifts or carts or all sorts of like different cleaning machines. Really, our modern supply chain depends on those machines. Right now, we are actually facing a very severe labor shortage in this space. And it is quite obvious that sooner or later, a lot of these machines are going to have to become autonomous. Just as a reference, just to kind of paint the picture for you, there's around 1 million forklifts being shipped to customers globally per year right now. So 1 million. And there's around like a couple of thousand, like 4,000 of these are somewhat automated. So that we're talking about 0.2% automation rate. And the reason why of course this technology, why we actually haven't seen a very large number of these super flexible, highly perceptive autonomous mobile robots already swarming our average industrial spaces is really because of the limitations of the technologies, especially perception technologies, which we are now starting to actually break through. Of course, COVID-19 hasn't helped the situation. The labor shortage is actually accelerating. Of course, we are now in a very all of the kind of supply chain players out there are actually facing difficulties on many levels. Of course, health is a primary preoccupation for those companies and their workers, because worker health has really become the paramount objective in this environment, which again makes it difficult for the supply chains globally to actually sustain the throughput they had previously before COVID-19 hit. And basically what's quite important is the realization, of course, that the COVID-19 is rapidly accelerating the rise of robots, especially in the autonomous mobile robotics space. We are seeing that across the spectrum, across the market, in all sorts of different autonomous mobile robot subsegments. Whether we talk about machines that are focused on indoor environments, or we're talking about last mile delivery robots combining indoor outdoor type of operations, we're seeing a huge acceleration in interest for these types of technologies, which we believe will, of course, will actually transition into aggressive adoption in the coming months and years. And let's start with several fundamentals. I mean, when we talk about self-driving robots, and that actually goes for all sorts of self-driving robots, whether we're talking about self-driving cars driving 90 miles per hour, or low-speed 10 miles per hour autonomous forklifts or autonomous turtle bots inside of a warehouse. We're talking about some very basic spatial problems we need to solve. We need to figure out, the robot needs to answer the question of, where am I in the space? Like, it needs to figure out its location in the space. It needs to understand what are the objects, where are the objects around him, how far away they are from it. And ultimately, it really needs to understand what are those objects so that it can interact with those objects. And of course, there are all sorts of other problems we can mention here, like, okay, when we understand where are the objects and what are those, how do we actually get around them to get from point A to point B, which is the problem of actually navigating through a complex space. Or we can talk about a problem of how do we coordinate with other machines which are also in the space. But so all sorts of different problems. These are really the fundamental ones we focus on. And just wanted to give you a very brief overview or like a description of how the low-speed robot autonomous systems developed over the time. So first of all, these technologies actually started as a pretty much kind of superstructured guided systems, so-called AGVs, or automated guided vehicles, which actually are out there on the market for decades, almost 3 decades or more. These systems basically have been following predefined routes, basically rails or markers, codes on the floor or on the walls, so that they can actually figure out their location. Of course, the disadvantage of those systems, and the reason why they actually haven't penetrated the broader market, is that they are super structured, they are super inflexible, and they are super expensive because they require a significant investment into adaptations of the infrastructure so that these machines can actually operate in this space. Those systems have evolved a little bit more over the past 5 years or so into a somewhat more flexible machines that are powered by 2D LiDAR systems. 2D LiDAR brought flexibility to those machines because a 2D LiDAR based scan of a 2D plane in the environment really helped us answer some of those original spatial questions I brought up at the very beginning. The problem with LiDAR, of course, which is something we're going to get into, is that it's just simply limited, especially when you need to work in very large, very open, complex, constantly changing, dynamically changing environments. That's where 3D, basically vision, comes into play. It's a very young technology. It has just started ramping up. There's a very few companies globally working on this approach. Maybe the most famous one from the self-driving car market is Tesla, who's betting on cameras to solve the fundamentals of the autonomy. They're having a more difficult problem trying to do that, driving 90 miles per hour. So it's definitely an exciting era, and we're now seeing where we're now actually entering an environment where visual autonomy is becoming much more popular with different machine OEMs who really understand that if they want to build fully flexible, low-speed autonomous mobile robots, that they need to start equipping them with visual perception capabilities. And we believe that within 5 to 10 years' time, so 3D visual autonomy is really going to become the standard of this industry. Just going back to LiDAR, some of the challenges we've been observing, of course, obviously, like 3D obstacles are not visible to a simple 2D LiDAR. And just to explain why 2D LiDAR has been the kind of choice to achieve this next stage, evolutionary step in the development of autonomous mobile robots. Of course, when you start developing these vehicles, you need to build vehicles that are commercially attractive, that are actually that it actually makes sense from an ROI perspective for the end customer to buy those and implement those. We could, of course, slap 3D LiDARs on top of these machines, but that just doesn't make sense from an economics perspective. So there's a balance between the cost of the machine and the benefits we're getting out of it, especially if it's a very limited machine which cannot solve all of our automation goals or all of our automation targets inside of a, let's say, closed industrial environment. So of course, 3D obstacles not visible. There are significant problems, and this is probably the most important limitation of a 2D LiDAR-based self-driving robot. These systems are just having difficulty localizing themselves, figuring out where they are in very large, open, constantly changing environment. So if you imagine a large third-party logistics warehouse, like a cross-dock, for example, warehouse or a cross-dock warehouse, those are large spaces. They have parts of those facilities that are very open. You can have hundreds of pallets sitting in front, in the middle of those spaces, and in 10 minutes they're not there. So a 2D LiDAR scan really doesn't have enough reference points to actually localize itself within that kind of open, unstructured, highly dynamic environment. Of course, LiDAR ultimately has serious issues with actually detecting and tracking of moving objects. Again, it's really important. Why? Because some of the objects that are actually appearing in the robot's field of view under or above the LiDAR beam is not detected by the 2D LiDAR scan. So if we cannot understand, if we cannot track those 3D objects, we just don't have a full understanding of the environment, and it actually can cause damage, which was often the case when these systems were being tested inside of these large, complex facilities. They were not robust enough to actually understand 3D objects in this space, which sometimes cause them to crash into things, for example. Of course, not understanding like holes in the ground, all sorts of uneven surfaces is a problem which can be also solved by visual information. So that's where we come in. We basically have tried to solve this problem, each and every one of those problems, with the use of visual information. One of our major customers is one of the world's largest 3PL logistics operators, so DB Schenker out of Germany. So I'm just gonna quickly start a video which gives a very brief overview of all the major components of that system, which we're gonna get into later. Of course, it's really paramount for the system to understand its environment, 3D environment, semantically. to actually differentiate between different classes of objects in the space, because it needs to interact with those objects differently. Each object class or type is different. Of course, we need to understand our world in 3D. We need to reconstruct the map of the environment in 3D using natural features of the 3D space, while understanding which features can be used for map building, which features are actually static and there for good, differentiating them from all the features that are dynamic, that belong to forklifts, humans, and all sorts of moving objects that are not going to be there next minute. So ultimately, just kind of simplify things, the visual approach to a low-speed vehicle autonomy simply enables robots to be more flexible, which means they have a greater degree of understanding the geometrics, so spatially understanding the world, simply because they have much more reference points to draw conclusions around their location in the space. They can be more productive, which meaning they can actually understand the objects they need to interact with in the space. For example, an autonomous mobile robot can understand that there's a pallet or some kind of cargo sitting somewhere in the space. If it recognizes that particular type of cargo, it can approach it and pick it up. That's a very obvious example, of course. Of course, it makes the system a lot safer, because all those machines are equipped with safety certified emergency stop technologies. 2D LiDAR is actually an example of such a technology. There are some other ranging technologies that can be used instead of a 2D LiDAR, ultrasonic, for example. But the whole point is in actually making sure that this emergency stop trigger never happens in the first place, because that significantly reduces the efficiency of the process. Why? Because if you have lots of dynamics in this space, and these robots are constantly stopping as they face these roadblocks and obstacles, they're not going to get to the destination, and they're going to cause trouble for all sorts of other machines that actually need to operate in the same space. So close collaboration with humans is a prerequisite for a successful implementation of these machines into our average industrial facility. So if we understand that there's a potential safety incident that might happen 20 meters down the road, but we do not get closer to that potential situation, we figure out a way to get around it. We don't make a stop for 30 seconds or a minute until all of that gets resolved on its own. We actually save time and increase the efficiency of the process. Those systems are obviously faster and easier to deploy. Why? Because the system is designed in a way that the end customer really needs to take this machine, drop it into its existing process, and have it functional and operational within a few hours, which is quite different from older generations of technology, especially in the AGV era, where you had to invest lots of money and months of time to actually retrofit the space and make it ready for the implementation of these systems. Ultimately, of course, it's a lot cheaper to manufacture because we believe that well-designed, low-cost or lower-cost visual sensors are as the primary source of information about the robot's environment, are actually going to become the standard of these types of vehicles. So just to get into a little bit more details here, I'm actually going to be showing some videos and trying to describe some fundamental components of what I just described to you. everything really depends on our successful building of the map of the environment and localizing ourselves or the robot inside of that map. That's kind of really the starting point. And our system is capable of doing that both in 2D and 3D perspectives. So we're merging those two perspectives. We are, of course, then adding semantic information to those maps so that we can actually figure out which types of features that we encounter in those space can be actually used for map building purposes. And ultimately, we use that information also for navigation purposes because we need to understand why, we need to understand the dynamic obstacles we face on our traversable path so that we can calculate the optimum navigational route for to get to our destination. We actually need to use all sorts of different supportive technologies and tools that allow us to build such a system. For example, we have different simulation engines. So these are realistic environments that are emulating the sensor capabilities and the machine's behavior inside of a some kind of spatial scenario. We, on the machine learning level, we had to design basically a pipeline of tools and processes that actually help us gather and prepare enough data to train our machines on how to differentiate between different classes of objects they're going to be facing in the environment. So, for example, we built an annotation engine. We have a team of data annotators that are actually helping us generate a good data set for that is to be fed into our machine learning training models so that our machines can get better at understanding different classes of objects they're going to be facing in their environment. And at the base of it, of course, is the visual information itself. So the sensor, we've developed an extendable stereo vision system, which can be extended, of course, into multiple stereo vision pairs. Even mono cameras can be added to such a configuration depending on what the vehicle actually requires. What is the form factor, the physical robot you're trying to actually achieve this capability for? It's a passive system which basically provides an RGB and depth data stream for us. Stereo depth estimation is at the very core of this approach because it allows us to emulate the ranging capability of a traditional LiDAR-based system. We designed it, of course, from scratch for low visibility conditions. And we've been testing out different stereo vision systems, off-the-shelf systems on the market, but we've just learned through experiments that they were just not good enough for what we wanted them to do in a very low visibility, bad lighting, lots of reflections type of environment, which is a traditional industrial environment. So going a little bit deeper into that base component, into that fundamental component, which is the 3D SLAM. So we're using a sparse feature-based approach, which means that for the visual SLAM purposes, we don't need a full 3D reconstruction of this space. We actually only need to determine or extract the most important features of the space to feed this algorithm. There are basically three core aspects or three core pillars or evolutionary steps of this piece of technology. One of them is of course, completely automated building and updating of maps, which means that once the initial map, 3D map has been built, the machine needs to have the ability to constantly update the map. That is quite important, of course, because the map might change in 10 minutes time. The second pillar, or second step, is basically embedding semantic information into the map, into the SLAM procedure, because we again need to understand what are the dynamic and static objects that we can reference ourselves against, and ultimately we need to work with other robots in this space to collaboratively basically contribute to the map building process. I'm just going to show you a quick video of the sparse, of a sparse feature based SLAM algorithm output we have built, which we actually based our core algorithms on. So it's basically you can take a look at what happens here. Just a sec. When the loop closing procedure happens. So you can see the robot goes around, it builds the map, it tries to find the right features, extracting the right features. Okay, so this is where it happened. So you can see it reached a location where it has previously visited. It recognizes the features of that location, and it basically automatically adjusts the whole map of the environment. Quite important.
Please have the time, consider the time. You have to come to the end soon. Thank you.
Sure. Yep, go ahead. This is just another simple example of that approach. It is just a different view of that same algorithm output. We also use, I'm just gonna give you a quick overview of a 3D reconstruction procedure. We also use 3D reconstruction, of course, but primarily for application-specific purposes. So we need to understand the 3D dynamics of the environment so that we can figure out exactly the places or objects of interest we need to interact with in the space. And of course, depth estimation, something I've already described. I don't want to get into a lot more details, but this is basically the output of the RGB output and the depth estimation output of the visual sensor itself. Deep learning also, I've also made some references to it, but it comes down to semantic segmentation and object detection. Just gonna give you a quick video of how that looks like, how the robot semantically understands its environment. So it basically tries to segment all of the major components of the space into digestible objects. So all of these colors represent objects that are known to the robot. So you can see the human being recognized here, a traversable, this large blue floor is basically a traversable space, traversable floor for the robot. It recognizes racks, it recognizes pallets and the cargo on the pallets. So this is the result of a machine learning training procedures. Another view of it is the actual recognition of particular objects in the space on an object level. And I'm just gonna move fast forward to the next video, which is basically a combination of the two. So it basically, besides the bounding box, we can actually do a contour-based recognition of the actual cargo, of the actual object. So again, that we can actually interact with it in a better way. We use a lot of synthetically generated data, where we actually have a team of artists that generate artificial worlds that our robots are also trained on, which is quite important if you want to generate variability of the spaces these robots ultimately need to get into in the real world. This is just an example of images, which are real images and quite photorealistic artificial generated images that our robots are trained on. And ultimately, just wanna maybe skip to the last video. This is how it looks like. So the robot approaches a low-hanging 3D obstacle, and it simply nicely maneuvers around it. That's the whole point. Again, we're a team of around 60 people based in Zagreb, Croatia, and looking forward to addressing your questions. Hopefully that was not too long.